Okay, it is time to get started on Unit 16C in our 211 class. And back to our same chart. Okay, A, B, C, here we are. All this stuff still holds at the top. This is out for now. We're talking about pendulums. Pendulum, the restoring force is gravity, not anything elastic. So owing to what we did last time, we expect something elastic over something related to the mass. On top is little g, as expect, that's gravity force related. On the bottom, moment of inertia, remember, has an ml squared. And so it's that L on the bottom that comes up. In fact, the restoring force is mg, right? So ml is not really that surprising. And in the T pendulum, of course, you flip that. The energy total is now all be in kinetic, or it can all be in potential, which is mgy max. Remember, we got a pendulum here. We start at the bottom. We swing up to y max. We swing back down to the other side. So again, we do this transversion from potential to kinetic, to potential to kinetic, potential again to make one cycle. And that vertical distance is what matters for the potential. So you can't see it very well, but if I take my handy dandy yo-yo out and manage to keep it from being a yo-yo for a minute so we can make pendulum out of it, and then you get, right, here it is, here near the thing, we swing it back and forth. And as we swing it, it goes up, it goes down, and the thing doesn't track it very well. Maybe if I swing it this way, it would do a little bit better job of doing that. And so what we want to know is what happens. And it's clear if we make this shorter, so I pull it up closer to the camera, it gets faster. And if I make it longer down here, it's pretty slow. Pulling it up here, it's obviously much faster. So if we make this shorter, smaller on the bottom, faster on the top. If we go here at a small amplitude, you get a certain rate. If we go to a larger amplitude, it's actually the same rate. If you go and look at it, it's just that we go faster because we have a bigger amplitude. But it's the same frequency as we did the smaller one. And that's because it's the same L. There's no amplitude in this. So that is something to keep in mind. Now, this, of course, is part of a more general case, which you've seen before. Oh, come on, thing. I have to constantly do this. You have to kind of feed it downwards here. Okay, so our physical pendulum is more general case. We have tau is equal to I alpha. And so we can write this as a torque for a particular force is equal to L F sine phi, where this is our R is equal to L, length of our pendulum, as it were. And so if we now write this out, I alpha on one side is equal to L mg sine phi. So what does this mean? It means that our gravity restoring force and so if we write this slightly different, we can write that alpha is equal to mgl over I times the sine of phi. And if phi is small, this is approximately equal to mgl over I times, well, let's call this theta because why not? Theta. And so, look, alpha, this is like x, and this is like A. And so we can pull off omega straight from this. So these two together imply that omega is the square root of this mgl over I. And if you, so this is the general case. So if I give you any moment of inertia, and this L is the distance to the center of mass, right? So let's think about this. mg, that's restoring force. L is the distance pivot to center mass distance, and I is the moment of inertia about the pivot point. So you may have to use the parallel axis theorem to get it up there, because it's not the center mass, because the center mass is down here, distance L. It's not going to be at the center mass. We'll be parallel to it though, and so you're going to have to use the parallel axis theorem to get it. This is about the pivot. Okay, so if we simplify this now for our simple pendulum, then we have I is equal to ml squared, and so omega is equal to the square root of mgl over ml squared, and lo and behold, what happens? That cancels, that goes with one of the squares, and you get the square root of g over L. That's what we have. Whoops, there we go. So I is equal to ml squared, plug that into here, ml squared at the bottom, m's go, square goes with that one, and get g over L in the square root. That's exactly what we had for the simple pendulum before. So this is how you get there generally, and if you ever have something that isn't simple, like you hang a hula hoop up on a nail on one side, okay, you know the hoop's moment of inertia about the center, you shift it with parallel axis theorem to about the edge of the hoop, and you plug that in here, and L is the distance down to the center of the hoop, center of mass, and you can easily solve that thing for the frequency. And so that is where we start. But we are going to stick in this class to the simple case. So here we got a grandfather clock. It uses a simple pendulum. In reality, of course, they're all using I pendulums, complex ones, but ours is simple. It's just like our little swinging yo-yo here, which you can approximate very well as a point mass. So which will happen if the 5 kilogram mass is doubled to 10 kilogram? Speed up, slow down, keep the same. Pause the thing until you come up with an answer. Boom, I assume you have, if you're here. So you write down omega is equal to square root of g over L. You know what happened to the masses? They canceled out. Where did they cancel out? Right here, that's where they canceled out. They're gone. And so stays the same. No mass. For the simple pendulum. Okay, part 2. Same problem. What will happen if it's moved closer to the pivot of the pendulum? Okay, so we have something down here, and now it's here. Again, omega is equal to square root of g over L. And if L is smaller, this gets bigger. So L down, omega up. So it speeds up. And there's another way that you can solve this. It's sort of if you have trouble with these qualitative, put in numbers. All right, so L initial is equal to 2, L final is equal to 1. Omega initial then would be square root of 5, 10 over 2. Omega final is equal to square root of 10. And you say, oh, let's see, we shortened it. Yeah, the frequency is higher here. And the time, by the way, is, so the t is equal to, remember we have to do this correction because it's sort of, when you say long, speed up, slow down, you're really talking about time. And so you want to have time is 1 over f is 2 pi over omega. And so that's, if you ignore the 2 pi, it's 1 over this. So it goes, t initial is like 2 pi over the square root of 5, and t final is 2 pi over the square root of 10. And then you see, okay, t final is less than t initial, so that's kind of, it speeds up, less time. So depending on which way you want to think about it, higher frequency is speeding up. Why? Because frequency is 1 over period. If that helps you think about it better, then think about it that way. T is equal to 2 pi the square root of L over G. So L down, time down faster. So depending on how you want to think about it, some of you will say, well, higher frequency is sped up, and others will say, no, I want the period. I want to see a shorter period to speed up or slow down. Either way is fine, so long as it works. Okay, now let's go on to the next one here. What happens if the displacement of the swinging arm is decreased? Well, you kind of get the picture now, right? Let's just start with this one. T is 2 pi the square root of L over G. And there's no theta in here for simple harmonic motion. I say that because if you actually swing too far, so for the pendulum, you can't swing the pendulum too far, or sine theta equals theta, not right. So not simple harmonic motion anymore. But as long as you stay within the duration, it is simple harmonic motion. There's no theta in there, and so it keeps the same time. Okay, so number 4, which same pendulum again, same setup. Now we move the grandfather clock from Raleigh to Mexico City. And since I guess we did the first couple with frequency, 3 we did with time, we'll do time again for those of you that prefer that. So again, t is equal to 2 pi the square root of L over G. Again, those of you that like it the other way, omega is equal to square root of G over L. And so G is on the top here. So if G goes down, it's on the top. Omega goes down, so that's slower. And over here, G is on the bottom. So if G goes down, T goes up. And that says it's slower. And either one says it's this. There's even a third way you can do this. And you say the restoring force decreases, since, that's mg. And so that means it's slower. So slower recovery, slower everything. Okay, and now that brings us to part 5. Same problem at the top. The period of the clock's pendulum is 2 seconds on the Earth. What's the length of the swinging arm? Okay, so I guess this case we have no choice. We'll use this one. T is 2 pi, the square root of L over G. And of course, remember that omega is equal to square root of G over L. Omega is also equal to 2 pi F, which is 2 pi over T. And you should have all of these parts safely tucked away in your sheet or in your head. And so that's how you go from here to here. But now what we want is the length of the swinging arm. And so we can get that by squaring both sides. First we divide by 2 pi t squared over 4 pi squared is equal to L over G. So L is equal to t squared G over 4 pi squared. And if you plug in the numbers, you find out it's 0.99 meters. And that is all that we have for 16C. Next time we're going to come back with 16E. We skipped 16D, which is the damped oscillations, and moved to 16E, which are waves, with our next unit. Right now, we are done. See you later.